Hi students, welcome to SankalpStudySuccess. I am Tirupati Rao. Please subscribe our channel. So in the previous videos, I discussed about bond parameters like bond length, bond angle and bond order. Now we will discuss about bond energy or bond enthalpy, or it is also said to be bond dissociation energy, BDE, bond dissociation energy. So right, so what is bond energy? So listen to me. So suppose we can take in 1 mole of any gas, 1 mole of any gas. This is the 1 mole of H2 gas. So this H2 gas containing H2 molecules, hydrogen molecules. So in hydrogen molecules, this hydrogen molecule is present in H bond H. So some of the energy is required to break this bond. So that energy is said to be bond energy or bond enthalpy. So this bond is also a particular type. Suppose here the bond is H bond H. So suppose we can take an ethylene C2H4. In C2H4, different types of bonds are there. C bond H and C double bond C. Here different types of bonds are there. Here C bond H is one type and C double bond C is another type. Right. So the amount of energy is required to break 1 mole of bond of particular type. That particular type means C bond H or C bond C. Particular type of bond of particular type between atoms. These two are atoms, between atoms in a gas state. That substance must be present in a gas state. So that energy is taken as bond energy or bond enthalpy. So what is that? So this is the 1 mole of gas. It is containing it is a hydrogen gas. It is containing H2 molecules. So here H bond H. So some amount of energy is required to break this bond. So that bond is said to be bond energy or a bond enthalpy. Here bond is which type of bond? Particular type of bond. That particular type of bond in the present in ethylene are two types. So C bond H and C double bond C. So that energy is said to be bond energy or bond enthalpy. So once again, the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. So is known as bond energy or is known as bond energy or bond enthalpy. Bond energy is represented by BE or bond enthalpy, right? So suppose this is the H2 molecule. This is present in gaseous state like H2. So some amount of energy is required to break this H bond H. So that will convert to, when the hydrogen bond is break down, that will convert it to H atoms. How many H atoms? 2 H atoms. That is also present in gaseous state. So how much amount of energy is required? 436 kilojoule per mole. So this is a negative. Okay, the delta H value is present in a positive value. So that is endothermic. Endothermic means energy is required, right? So right, the units of bond energy is kilojoule per mole or kilocalorie per mole. This is the energy. So its units are kilojoule per mole or kilocalorie per mole. So how much energy is required to break H bond H? So 436 kilojoule per mole. So its bond energy or bond dissociation energy or bond enthalpy is 436 kilojoule per mole. Next, bond dissociation energy is considered as negative. Bond dissociation energy. So bond dissociation energy is considered as positive values. Bond dissociation energy is considered as positive values because some amount of energy is required. Energy is required to break that bond. That means energy is supplied. Energy is supplied means its value is taken positive. Energy released means its value is taken as negative. So bond dissociation energy is considered to positive values because energy is supplied. Energy is supplied. Next, it is generally observed that shorter the bond length, greater the bond energy. So we know that. So shorter the bond length, greater the bond dissociation energy. Suppose this is the H bond H, hydrogen. Its bond length is 74 pm. 74 pm. 74 pm. Its bond length is, what its bond length? 74 pm. Pm means picometer. Here chlorine. So this is the 198 pm. Its bond length is 198 pm picometer. So in these two, the bond length of Cl2 is more than that of H2. So due to this is the small size atoms, this is the its size is high. When the size is increases, when the size of the atoms increases, its bond length is increases. And also if the lone pairs present on atoms increases, bond length is also increases. Here are no bond pairs. Here bond pairs are present. Here lone pairs are present. If the lone pairs on atoms increases, then the bond length is also increases. So in H2 and Cl2, which is having more bond length? Cl2, due to more atomic size or repulsive between the lone pairs. Now, so here it is a less bond length. Its bond dissociation energy is 436, but it is having high bond length. Its bond dissociation energy is less. That means if the bond length is increases, bond dissociation energy is decreases. Bond length is increases means that is a weaker bond. If the bond length is increases, that means weaker the bond. Weaker the bond means its bond dissociation energy is less. So if the bond length is shorter means that is the strongest bond. So high amount of energy is required to break that bond. Right? Shorter the bond, higher the bond dissociation energy. So longer the bond dissociation energy is decreases. Now goes to another point. So as the number of bonds between two atoms increases, the bond dissociation energy is increases. So this is the single bond. So a less amount of energy required to break this one. So these are three bonds. These are three bonds. So high amount of energy is required to these three bonds. So if the number of bonds between two atoms increases, as the bond energy is increases. Here the C single bond C, here one bond is present. Here C triple bond C, here three bonds are present. So this is the stronger bond, this is the weaker bond. So which is having higher amount energy, which is required to high amount of energy? So C triple bond C. So here the amount of energy is required to break one bond, but here the amount of energy is required to break three bonds. So how much? 828 kilojoule per mole, but it is 341 kilojoule per mole. Okay, as the number of bonds between the atoms is increases, the bond energy or bond enthalpy or bond dissociation energy also increases. Next point, lone pairs on bonded atoms increases, the bond energy is decreases. Lone pairs on bonded atoms increases, the bond energy is decreases. So we know that one thing, here the C single bond C, so lone pairs are absent. Here N bond N, it is containing one lone pair on nitrogen atoms. O bond O, it is containing two lone pairs on oxygen atoms. We know that when the lone pairs on bonded atoms increases, repulsive force between the lone pairs are also increases, then the bond length is decreases. We know that if the bond length is increases, bond energy is decreases. If the bond length already says that if the bond length is increases, bond energy is decreases. Bond length is increase means that is weaker the bond. So less amount of energy is required to break that, right? So lone pairs on bonded atoms increases, bond energy is decreases. Why? So if the lone pairs on bonded atoms increases means a repulsive force on bonded atoms also increases, then the bond length is decreases. Finally, bond length is increases, and its bond dissociation energy is decreases. So lone pair on bonded atoms increases, the bond energy is decreases. Next point, in the case of H2O molecule, the enthalpy needed to break the two OH bonds is not same due to different chemical environment, right? So here this is the H2O. So these two are OH bonds. These two are similar OH bonds. This is one OH bond. This is another. How many OH bonds are present in H2O? Two OH bonds. So these two OH bonds are similar, but its breaking, its dissociation energy is also similarly same, but the bond dissociation energy of these two OH bonds are not same due to, if the O bond H is break, what is obtained? H and OH is obtained. So in the previous case, its surrounding the OH bond, its surrounding hydrogen is present, but now the O bond H surroundings hydrogen is not present. So these two are present in different environment, different chemical environment. So this is also OH bond, this is also OH bond, but in this OH bond, its surrounding hydrogen is present, but in this OH bond, hydrogen is not surrounding. So these two are present in a different chemical environment. So if the bonds of chemical environment is different, its bond dissociation energy is also varies, right? So in the case of H2O molecule, the enthalpy needed to break the two OH bonds are not same due to different chemical environment. Now suppose what is the example? H2O, it is present in gaseous state, right? If the bond is breakdown, what happened? HOH. So how much amount of energy is required? Its delta H1 is equal to 502 kilojoule per mole. Now here the OH is also again taken, this is present in gaseous state. So some amount of energy is required to break that O bond H. So what its value? 427 kilojoule per mole. So these two are different. These two OH bonds are same, but its bond dissociation energy is different due to different chemical environment. So now the bond dissociation energy of OH bond in H2O. Now the bond dissociation energy of this particular bond of OH bond in H2O molecule is average the two bond dissociation energies. Average means, so 502 plus 427 by 2. So how much? So 7, 2, 927 by 2. That means 2 1 ja, 2 4 ja, 2 6 ja, 2 3 ja point. So 463.5 kilojoule per mole, right? Kilojoule per mole. So in the case of H2O molecule, the enthalpy needed to break the two OH bonds is not same due to the different chemical environment, right? Similarly, CH4 molecule also. Now we can take in CH4 molecule. Similarly, we can take in CH4 molecule. CH4. CH4 means C bond H, C bond H, C bond H, C bond H. Right, tetrahedral shape. So here all the four C bond H are similar. Here all in CH4 molecule, all the four C bond H are same, but its bond dissociation energy of C bond H is not same. Suppose we can take in CH3 bond H like CH4, its bond dissociation energy is 106 kilojoule per mole. So it is break down CH3 plus H. This is present in gaseous state. These are also delta H1 can be taken as 106. Now we can take an CH3 that can be written as CH bond H. So these are converted to CH2 and H. Here 104, and again we can take an CH2. CH2, it is present in gaseous state. This will converted to CH plus H. This also having same bond dissociation energy. Again CH bond in gaseous state, that will convert it to C plus H. So if the C bond H is breakdown, that will convert it to C and H. C and H. Finally we got C and H. Finally we got C and H. So here it is having 81 kilojoule per mole. Now all these are bond dissociation energies. So all these are bond dissociation energies. So bond energy is the average of bond dissociation energy. Bond energy is the average of bond dissociation energies. That is very, very important point. So what is that? Bond energy is the average of bond dissociation energies. Average of bond dissociation energy. Now for the bond dissociation energy of C bond H, the bond dissociation energy of C bond H in CH4 molecule, C bond H in CH4 molecule, in CH4 is equal to average of bond dissociation energies, So now average means these are 4 by 4, 106 plus 104 plus 104 plus 81. So is equal to, so that means 210, 314, 315 plus 85, 9. So 395 by 4. 395 by 4 means, so 4 9 ja and 36, 35, 4 8 ja 32, 98.7 kilojoule per mole. So this is the bond energy or bond enthalpy of C bond H in CH4 molecule. So what is that? The bond energy or bond enthalpy of any molecule is the average of bond dissociation energy. Now the bond dissociation energy of C bond H is equal to 1 by 4 of bond energy. Yes or no? Bond energy is equal to 1 by 4 of bond dissociation energy. But bond dissociation energy is equal to 1 by 4 of bond energy. Next. Next goes to bond energy is directly proportional to bond strength. Bond energy is directly proportional to bond strength, and bond energy is inversely proportional to bond length. Bond energy is inversely proportional to bond length. We know that, already says that if the bond length is increases, it is a weaker bond, so less amount of energy is required to that bond. So that means bond energy is decreases. So okay, longer the bond, weaker the bond dissociation energy. Okay, lesser the bond energy. Next, bond energy is inversely proportional to reactivity of substance. If the bond energy is more, means that is the stronger bond. That means its stability of bond is more. Stability is more means reactivity is less. So bond energy and reactivity are present in inversely proportional. If the bond energy is more, its reactivity is less. Next goes to one sum on this concept. Right. Dissociation enthalpies of methane, ethane and ethylene are respectively 400, 680 and 540 kilocalorie per mole. Calculate the sigma C bond H, sigma C bond C and pi C bond C bond energies. So listen to me. So here bond dissociation energies of methane, what is the formula? CH4. So that means C bond H, we know that. In CH4, how many C bond H's are there? How many sigma CH bonds are there? 4 C sigma bonds. So that means the bond energy, therefore the bond energy of sigma C bond H. So it is containing 4 sigma C bond H's. We know that the bond energy is equal to average of C bond H's, average of bond dissociation energies of C bond H. Now here the how many C bond H's are there? 4 C bond H's. So the bond dissociation energy of 4 C bond H's is equal to 400. So now we want to the bond energy of sigma C bond H is equal to 400 by, it is containing how many C bond H's? C bond H 4. 400 by 4 means 100. What its units? Kilocalorie per mole. So this is the bond energy of sigma C bond H. We know that here the bond dissociation enthalpy of methane is given. So that is 400. That 400 is the bond dissociation energy of 4 C bond H's. 4 sigma C bond H's. But we want to the bond energy of one sigma C bond H is equal to 400 by 4. So that means 100 kilocalories per mole. Now next goes to ethane. This is methane. Now goes to ethane. So ethane, we know that as what its formula? C2H6. C2H6 means C bond C, H. So it is containing one C bond C and 6 C bond H's. So it is containing one sigma C bond C and 6 sigma C bond H's. But we want to bond energy of sigma C bond C of ethane. Now the bond energy, therefore the bond energy of sigma C bond C is equal to total bond energy of ethane. Total bond energy of ethane, how much given? Total dissociation enthalpy of ethane 680 minus, so this total ethane molecule containing 1 sigma C bond C and 6 sigma C bond H's. Okay, if you want to the bond energy of 1 sigma C bond C is equal to total bond energy minus 6 into sigma C bond H. Now we know that 680 minus 6 into sigma C bond H. The bond energy of sigma C bond H is equal to 100. 6 into 100. So is equal to 680 minus 600 is equal to 80 kilojoule per mole. So this is the bond energy of sigma C bond C. Now we can calculate the pi C bond C, right? So what is the another value? Ethylene. What its formula? C2H4. What its formula? C2H4. How can write? It can be written as C double bond C H. Therefore, it is containing how many C bond H's? How many? So it is containing 1, 2, 3, 4. 4 sigma C bond H's and 1 sigma bond. This is the sigma bond, this is the pi bond. This is the pi bond, this is the sigma bond. So 1 sigma C bond C and 1 pi C bond C. This is the 1 pi bond C bond C. So in ethylene, in C2H4 molecule, 4 sigma C bond H's and 1 sigma C bond C and also 1 pi C bond C is there. Now we want to bond energy of pi C bond C. So the bond energy B of pi C bond C is equal to, we know that the total bond energy of ethylene, how much? The total bond energy of ethylene or dissociation enthalpy of ethylene is 540. That is the total dissociation enthalpy of ethylene. That minus, it is containing 4 sigma bond CH and 1 C bond, sigma C bond C. So that can be subtracted. We got pi bond, pi C bond C. So 4 into 4 C sigma C bond H plus 1 sigma C bond C. Now 540 minus 4 into, we know that sigma, the bond energy of sigma C bond H, sigma C bond H is equal to 100. 4 into 100 plus 1 into, we also know that sigma C bond C how much? 80. So totally 540 minus 400 plus 80, like 540 minus 480 is equal to 60 kilojoule per mole. Right, this is the bond energy of pi C bond C. So this is over. Now goes to another sum. So bond energy is highest in the molecule. Bond energy is highest in the molecule. So F2Cl2, Br2, I2 is given. We know that the size of bond length is increases fluorine, chlorine, bromine, iodine. So this is the 70th group. In the group from top to bottom, the size is increases, the atomic size is increases. If the atomic size is increases, bond length is increases. That means so these are the, its size is very high, its size is very less. So its bond length is this bond length is this. So if the size of the atom is increases, its bond length is increases. We know that if the bond length is increases, bond energy is decreases. Bond energy and bond length are present in inversely proportional. So bond energy is inversely proportional to bond length. So in these two, iodine having more atomic size, its bond length is very high, so its bond dissociation energy is less. But fluorine F2, it is having a high bond dissociation energy. But in F2 and Cl2, Cl2 having more bond enthalpy than F2 due to the size of fluorine is very less. Its size is very less, but due to small size, so the lone pairs on fluorine atoms I repulsive. The lone pairs on fluorine atoms are I repulsive. So here fluorine having 3 electron pairs. This fluorine also having 3 lone pairs. So its size is very high. Then the repulsive force between the lone pairs is high. So its size is its bond length is high. Why its bond length is high? Its size is less. That means I repulsive force present between these lone pairs. So its bond length is increases. So bond length is increases. The bond length of fluorine is more than that of chlorine. So which is having more bond dissociation energy? Chlorine having more bond dissociation energy. So that is the answer, chlorine, right. The bond dissociation energy of molecules A2, B2, C2 are 498, 158, 945 kilojoule per mole respectively. So the correct decreasing order of their bond energies. So what is given? Bond dissociation energy is given. Bond dissociation energy of A2, B2, C2 is given. So what is bond dissociation energy? 498. This is 158. This is 945. So bond dissociation energies are given. Its bond order is asked. So bond dissociation energy and bond order and bond energy or bond dissociation energy both are same. Bond dissociation energy or bond energy both are same. Bond energy is the average of bond dissociation energy. So bond dissociation energy is considered as bond energy is inversely proportional to is directly proportional to bond order. So bond order means number of bonds between the atoms. The number of bonds between the atoms in a molecule is known as bond order. So bond energy is directly proportional to bond order. So bond energy is directly proportional to bond order. So which is having more bond energy, that is having more bond order, right? That means here which is having more bond energy, C2 having more bond energy. So its bond order is high. And next goes to A2, that is having 498. So next A2 and last one is B2. This is the bond order. Why? Bond energy is directly proportional to bond order. So which is having more bond energy? C2 having more bond energy. So its bond order is high. And which is having least bond energy? B2. So its bond order is less. So decreasing order of their bond energies. C2, A2, B2. What is the? So this is the answer. C is the answer. So which is having more bond energy? C2 having more bond energy. So its bond order is also high. And B2 having a right, C2, A2, A2, B2. So B2 having less bond energy. C2 having less bond energy. So its bond order is less. So this is the decreasing order of bond order. Thank you for watching. Please subscribe our channel.